Hello everybody and welcome back to this second video on logarithms should I say, and exponentials. So today, logs and exponentials part 2, we're going to talk about derivatives. We laid the ground for this in the previous video, if you remembered. Actually, let's start with a little recall here that we had last time. Limit as x goes to 0, e to the x minus 1 over x. That was obtained to be equal to 1. We did that numerically, and we call these guys special limits. So this is a special limit. We met some before. Remember, limit as x goes to 0 of sine x over x, also equal to 1. Special limit as well. So I'm going to need this now because I am going to be here in this little section. I'll be looking for the derivative of e to the x. Looking for the derivative of f of x equals e to the x. So this is the purpose of this first thing we're going to do together today. At the end of this explanation, I want the derivative of e to the x. And how am I going to get that? Well, remember that basically I should keep in mind that I have a limit definition that I haven't used in a long time. And when I don't know how to do a derivative, this is always a good fallback plan. So if you remember, try to, because the final exam is coming, and this is going to be on the final exam. That is the limit definition, not necessarily this very one I'm doing with you here, but the concept of. So what is my function here? F of x is e to the power of x. So what is f of x plus h? What is f of x plus h? Perhaps we start with f of x. What is f of x? Well, it's e to the x. What is f of x plus h? Well, we've seen that a million times before. All we got to do is replace x with x plus h. Here we go. X plus h. And as usual, if you actually cheat at this stage of the problem, you're going to get 0 over 0. So I'm not even going to do it because I know this is what I'm going to get. So how could I do this? Well, I have a special limit, and I intend to actually use it. So how do I use it? Here's the trick. You want to break e to the x plus h into e to the x times e to the h. That is e to the x plus h, because when you multiply two things that have the same base, you add the exponents. Minus e to the x over h. And then that gives us a nice little piece of algebra in the numerator. There is now a common term between the two halves. So that's the limit as h goes to 0 of, I'm going to take out that e to the x and be left with e to the h minus 1 over h. Now notice, that limit is active on the variable h. It actually asks this function, its y value, what is it getting close to when h approaches 0? So it is completely independent of this guy. This guy has no h in it at all. This does, but not this. So you know why? Because this guy here doesn't have an h in it. I'm going to treat this as a constant. And what can I do with a constant? I can pull it outside of the limit. Oh, now ain't that sweet? Ain't that just so freaking lovely? Because check it out. Limit as h goes to 0 of e to the h minus 1. What is that? It is this, where x has been replaced with h. So this whole thing is 1. And this is a remarkable function. F of x is this now, f prime of x. So e to the x times 1 is e to the x. And at the end of the day, what have we done? We found that the derivative of the function e to the x is e to the x itself. Ha! The derivative of e to the x is itself. It is clearly the only function in calculus that has this property. The limit of e to the x is just itself. Let me show you on an example what I can do, we can do, should I say, with this. So, petit exemple, exemple 1. For those of you keeping track, 2.5 stars. Find the derivative of e to the x times e to the x. Aha, e to the x times e to the x. That is an important little thing. It's a multiplication, which means we shall apply the multiplication rule. So the first one goes prime times the second one, not prime, and vice versa. The second one goes prime. Now we just saw that the derivative of e to the x is itself. So that's e to the x times e to the x plus e to the x, and there it is again, e to the x. Let's see if we can simplify this a little bit. Aha! Two things that have the same base. What can I do with the exponents? I can add, yes. That's e to the 2x plus, hey, again, e to the 2x. Oh, look, same term, e to the 2x plus e to the 2x, so that's 2. E to the 2x. Good. And that is a good simplified answer. Now follow me on the following track here. So, conclusion, e to the x times e to the x prime is this. Yeah? Now clearly, e to the x times e to the x, same thing as before, that's e to the 2x. So the derivative of e to the 2x is 2e to the 2x. Now, check this out. This is, you've seen me do this before. So e to the 2x, I'm going to put the 2 after the e instead. And I'm going to rewrite this as, what's the same thing as 2? 2x prime. Oh, what does that make you think of? Some sort of a chain rule. Conclusion, e to the power of anything at all, let's call it u, is going to be e to the u times u prime. So this is our first key formula. The derivative of e to the x being e to the x is important, but this is even more important because it covers a larger class of functions. So quick example, exemple 2. Quick example, let's make this one not too difficult. Find the derivative of e to your favorite function, sine x. What's the derivative of e to the sine x? Well, this is my u. Sine x is my u. So basically I'm going to apply the derivative of e to the u to be e to the u times u prime. So e to the sine x prime is e to the sine x. So the derivative of e to the u is itself times the exponent of e prime. So basically we are going to have here sine x prime like this. Yes? Okay. So what we have e to the sine x multiplied by cosine, and that's that. That's the answer to the derivative of e to the sine x. Not too hard, is it? All right. Good. So our first formula here that eventually I'll be adding to the list, the long list of what we have in terms of formula for derivatives. I'll be adding this onto the list. Now, consider another function. F of x is equal to ln x, semicolon. What is its derivative? What is its derivative? Don't worry, I'm not going to go through the limit definition again. I have a better way. Y is equal to ln x. If you remember the previous video, what is ln x the same as? Ln x is the same as log to what base? What's the special base of ln? If you answered in your head or out loud, depending on. If you answered e, you are correct. Ln is log to the base e. All right? You remember how to switch a log into an exponential? If you don't, this is how. E to the y equals the inside of le log. So that's e to the y equals 2x. Y equals ln x is the same thing as e to the y equals x. So let me prime both sides. What's the derivative of e to the y? Well, we just saw the derivative of e to the u is e to the u prime, baby. So that is e to the u, so e to the y times y prime, and the derivative of x is 1. So what's y prime? 1 over e to the y. Well, I think I can simplify this a little bit. Y prime is 1 over e to the y. What is y from the very beginning? Y is ln x. Now here's the thing. When you have e and ln x like this, basically they are inverses functions of one another. So that y prime, these are gone. All you have left is 1 over x. So, conclusion of this little demonstration is that the derivative of ln x, is equal to 1 over x. Interesting one, but basically we can tag along the chain rule version of this, chain rule version of this rule. What is the chain rule version of this rule? Well, we need to replace x with u. And as you probably know, whenever we do this, this remains. That's going to be 1 over, instead of x, 1 over u. And what is characteristic of the chain rule? You actually end up multiplying the answer by the derivative of the inside. So that is your inside, right? Just like e to the u, well, kind of like the exponent is inside the e in a certain sense. So we have two new rules, e to the u prime and ln u prime. Let us see if I can sort of make those come alive together in exemple 3. Let's make this 3 star. Z. Evaluate. What could we get? We don't need that anymore. We don't need that anymore. Let's derive e to the x squared times the ln of cos x. Evaluate the derivative of this. Okay. So once again, it's a product. Once again, it's a product. So the product rule is in order. E to the x squared. The first one goes prime, while the second one doesn't. And then we add the opposite. E to the x squared is not prime, and that is the ln of cos derivative. Okay, so this is my u, e to the u. So how do I derive e to the u? It's e to the u times u prime. Ln cos plus e to the x squared. Haha, what do we got here? That's our brand new rule. Ln of cos, this is the ln of u. What's the derivative of ln of u? We had just learned that. 1 over u times u prime. So 1 over u times u prime. So we have in fact a couple of more derivatives to find, and we're done. Final answer. Derivative of x squared is 2x. Allow me to put it in front. It simply looks better. It's not wrong if you leave it in the middle. It just looks less professional. And we want to look professional, don't we? Plus e to the x squared. 1 over cos times, anybody remembers the derivative of cosine x? If you answered minus sine x, you're good. Of course, this could be further simplified, right? Sine over cos is tan, so that could be mingled up together as a minus tangent, but let's not go there. We don't really need to. Okay, wow. So we have 2 brand new rules that concern the function e to the x, or e to the u, and the function ln x, or ln u. Let's put this down here. So let's summarize so far what we have been able to do in this short time. We've done a lot. So what do we have so far? So far we have that the derivative of e to the u, is e to the u times u prime, is e to the u times u prime. We also have the derivative of ln of u, that is 1 over u times u prime. Excellent. So these are 2 important rules that actually go at the bottom of the list, if you want, of all of the other rules we had. Remember, like rules 1 to 8, when 8 was the quotient rule, I believe. Then we went rule 9, 10, and 11 with sine u, cos u, and f of x to the power of n. These will actually be added up at the end of the lecture today. I will see if I have time to make a summary of that. If not, I'll do it in class. Now, I want to consider some kind of a little cousin rule for e to the u. Consider the derivative of a to the power of u prime. Now, I'm not going to go through the details of how this formula is obtained. I think we have enough details so far on the theory for this section. But if a is any number that is positive, not 0, okay? So this is a special rule for e, where e is 2.718, blah, blah, blah. It's a specific number. This is not a specific number. This is any number as long as it is a positive number, non-zero. If you want to derive something like this, here's the formula. A to the u, the derivative is a to the u, not a big surprise, it's pretty close to that, times u prime, not a big surprise, because this has a u prime as well, times, I'm just going to move that aside a little bit to give me some room to maneuver, times there's an extra little bugger particle that actually goes there when you're deriving, say, something like 2 to the u. And that is the ln of 2. Now keep in mind that this is good only when a is 0. And to top it all off, and this actually is exciting because it's the last rule of derivatives for the course. Yay. Also, the log to the base a. So remember, ln is log to the base e, where e is a specific number. This is going to be log to the base of any number, again, as long as a is a positive dude. So that's supposed to be a u. Let's do a better job doing a u here. So, comes up. So what is this? This is, oh well, it's going to follow very much what the ln was, huh? It's going to be like 1 over u times u prime. And just like this guy here, which is an a instead of an e, just like this guy has an ln a, well, the log, instead of a base e, has a base a, it's going to require an extra little bugger particle, which is going to be not ln a, but 1 over ln a. Again, I'm not going to go into the details on how this is obtained. It's not essential at this stage of the game, but I want to see if I can put them to good use in an example. All right, so brand new rules. You know what? Let's put them here. Let's put them here so I can get rid of that. We'll have a nice little summary here. So a to the u prime is going to be a to the u times u prime. So that's a u times u prime. And that little extra part, because it's not e, it's a, I need to multiply this with ln a. And here's the derivative for log base e of whatever goes inside any u at all. Qu'est-ce que c'est? Well, it's 1 over u times u prime times 1 over the ln of a. And there you have it. All right, there you have it. We can actually call these, what did we say? Quotient rule was rule 8, then sine was 9, cos was 10, we didn't have a number for tangent, and 11 was f of x to the n, so 12, rule 12, 13, 14, and 15. And these are all the rules of derivatives we will ever need in Calculus 1 and Calculus 2, because this will also pop up in Cal 2 if you take that course. Okay, that's all very good, but basically it's useless unless we know how to apply them. So, example. I owe you examples. So this is today example 4. Evaluate, so 3 stars. Evaluate. What shall we have? Evaluate something like this. E to the root x over the log base 3 of x squared. Evaluate this derivative. E to the root x over log base 3 of x squared. All right, so how do we do that? This, what's the first rule involved? This is a quotient. So yes, if you're thinking quotient rule, you are perfectly correct. What is the quotient rule? Remember the quotient rule. The top dude is the f, and the bottom dudette is the g. So the formula is f prime g minus fg prime over g squared. We know that. We know that for sure. So f prime g, so log of x squared base 3. So the derivative of the first but not the second, minus the opposite. E to the root x goes no prime, but log goes prime. So log of x squared base 3 goes prime. And all of that jazz is over the denominator squared. So log of x squared base 3. This goes squared. Let's call this a DNS, do not simplify, because in the end we're just going to have a bunch of things, so let's not get crammed up over the algebra. How do I derive e to the root x? So now you got to look at your list and think, okay, one of these fits the bill. What is this one? E to the something. Aha. E to the u. So the derivative is e to the u prime. And of course, it goes almost without saying, this is my u. So this goes, qu'est-ce que c'est? E to the root x times root x prime. The log, rewrite, minus e to the root x log base 3 of x squared. First of all, notice that the x squared is inside the log, so it is your u. And the log has a base 3. Oh, I think I made a mistake right here. It's log to the base a, not log to the base e. Please correct this in your notes if you're taking notes. I did not notice this. This is log to the base a, of course. Log to the base e is ln. So log to the base a. And it's exactly this guy, right? Log to the base 3. So 3 is my a, and a3 is a number greater than 0. So I shall apply this times 1 over u times u, which is x squared, prime, times 1 over the ln of a. The ln of a is the ln of 3 because the base of the log is a and a is 3, like a here that I put e before, but I was wrong. So am I done? I'm not done because I still have a prime here and a prime there. So I need to evaluate all of my derivatives before I can call it a day. This is, qu'est-ce que c'est? Oh, we've seen this a million times. This is x to the 1/2, isn't it? So that is going to be 1/2 x to the 1/2 minus 1. So minus a half. Log base 3 of x squared minus e to the root x, 1 over x squared. The derivative of x squared is 2x, and 1 over ln 3. I really want to be neat. I should not keep negative exponents in the picture, so I'm going to get rid of that. Final answer, I should have e to the root x log base 3 of x squared. The negative exponent, x to the minus a half, goes under. So you can have here x to the 1/2 or root x, up to you, minus, what's that, e to the root x. If you want, only if you want, you can cancel this x with the x squared, and you will be left with an x downstairs. So the 2 I can put here, and that is just ln 3 times x. So x ln 3. And that would be the simplified version if you want. Well, simplified. If I want to like really simplify some more, I could take a common denominator. But basically I won't. I will leave it like that. It's good enough. I've already simplified a little bit. It's plenty. So all in all, in a nutshell, this completes the section on derivatives of log and exponential. We have one more item to visit. In this section, it's called logarithmic differentiation, and that is the next video. I wish you well. Have a good rest of the day. See you soon.